Hello students, today we will discuss bridge rectifier circuits. This is one of the full wave rectifier. In the previous videos we have seen the center tap full wave rectifier. This bridge rectifier is the most popular, widely used, because here we don't need center tap transformer which is bulky. Here a simple step down transformer is used. But instead of 2 diodes in center tap full wave rectifier, here we need 4 diodes. So this is the alternative to the use of biphase circuit. Now let us analyze this during positive half cycle. As you know, always we will start from the positive half cycle and during positive half cycle this terminal will be positive and this terminal will be negative. Now let us check the diodes which are forward biased and reverse biased. This is the anode of D1, this is cathode of D4, this is anode of D3, this is cathode of D2. Now let us check the diodes which are on, off, forward biased or reverse biased. The anode of D1 is at positive potential than the cathode, so D1 is on. D1 is on. Now D2, let us check D2. Cathode is at negative potential, so D2 is on. D2 is on. Now D3 anode is at negative potential than cathode, so this is off, reverse biased, not conducting. D4 cathode is at positive potential, so D3 and D4 are off. A diode is said to be forward biased when the potential at the anode is more positive than the cathode. I repeat, a diode is said to be forward biased when the anode potential is greater than the cathode potential. How much it should be greater? The anode should be always 0.7 volts more positive than the cathode for a silicon diode. You know, for germanium diode, anode should be 0.3 volts more positive than the cathode. So during positive half cycle, D1 and D2 are on, D3 and D4 are off. Now let us check how the current flows. The current starts to flow from the positive here through D1 through the load resistance, through D2 back to the transformer. So it circulates like this. So this is the current flow through D1, D2 and RL. During the positive half cycle, the current will be carried by D1, RL, D2. The current flows through the RL. Definitely the voltage drop appears across the RL. So here you will get. So let us say this is output voltage. This is input voltage. So this is about the forward pass. Before going to the negative half cycle, here how to construct this? We have seen this now during the positive half cycle. So always start with one diode. We will call it as D1, then a load resistance, then through D2. So this is during the negative half cycle. So the current flows in this direction back to the transformer. During the negative half cycle, the current will flow through D3, through RL and D4. So naming D1, D2 because analysis will be easy. Then in the negative half cycle, D3, D4. But always current flows through the RL in the same direction. So how to remember? to write this circuit. So 4 diodes are connected in the bridge fashion. During the negative half cycle, the upper terminal of the secondary winding here, this becomes negative, this becomes positive during the negative half cycle. So anode of D3 is positive, so it acts as closed switch. D4 cathode is at negative potential, so D3 and D4 are on during negative half cycle. Similarly, anode of D1 is at negative potential, so it is reverse biased. D2 cathode is at positive potential, so D1 and D2 are off. So let us see how the equivalent circuit looks. Here the negative half cycle and negative terminal, this is the positive, this terminal becomes positive. Now the current flows through D3, RL, D4 back to the transformer. It starts from the lower end of the transformer through D3, RL, D4 back to the transformer. Just follow this dot. So current is flowing in the same direction in both the half cycles. So during positive half cycle, the current is carried by D1 and D2, and during negative half cycle, the current is carried by D3 and D4. At any point of time, 2 diodes will be conducting. So the voltage drop, the output voltage here, the output voltage across RL definitely will be the maximum voltage minus 1.4 volts. What is this 1.4 volts? 0.7 volt is the drop across one of the diode, and 0.7 volts is the drop across the another diode. At any point of time, 2 diodes will be conducting. Each diode will have a voltage drop of 0.7. So Vm is the maximum voltage. Vm minus 1.4 volts will be the drop across the load resistance. Here this is wrong, 16.3, actually this is 15.4 volts. Here we have considered 12 volts as the secondary volts. It is the root mean square value. Then the peak value or the maximum value will be root 2 into 12 volts. So approximately it comes around 17 volts. So if the peak voltage here is 17 volts, the drop here is 0.7, 17 minus 0.7, then through the D4, so 17 minus 0.7 minus 0.7. So here it comes around 15.4 volts. So the waveforms, here this is the secondary voltage waveform, plus 17 minus 17. Just now we saw how we got 17, because root 2 times 12 volts is the voltage across the secondary. So here you will get the peak voltage, 17 volts. Then the voltage across RL without the capacitor. Till now we have not discussed capacitor, so forget about the capacitor. The voltage across just RL, voltage across RL. The waveform here is like this. So initially here this is due to D1, D2, this is due to D3, D4, it repeats. Here the mistake is, once again, here 16.3. Peak voltage is 17 volts. So there will be a drop across one of the diode and one more diode. 0.7 plus 0.7, 1.4. So it should be 17 minus 1.4. So actually this is 15.6. So in the textbook it is given 16.3. You make the change, it is 15.6. Then we don't want this pulsated DC, we want to smooth this. We want to remove the ripple which is present in the output of the rectifier. And actually a perfect DC looks like this. But here this is unidirectional, that's it. So to remove the unwanted AC component in the DC output of the rectifier, We use a reservoir capacitor C1. So the property of the capacitor is to charge and discharge. So the capacitor starts charging towards the peak value. Then it discharges through the load resistance. After charging, the capacitor tends to discharge through RL. Once again, the next half cycle, it charges, again discharge, charge, discharge, charge, discharge, charge, discharge. So this is better than this waveform. So this peak to peak is nothing but the ripple. This is the change from higher peak to the lower one. So this is the ripple. The ripple has been reduced. Now we would like to regulate the output voltage of a rectifier. So always we want a constant. For example, 5 volts plus 5 volts. Always I need plus 5 volts. I don't need 5.1 or 4.8 etc. Then we should go for a voltage regulator. A regulator is a circuit where the output voltage always remains constant irrespective of the variations in the input voltage and irrespective of the variations in the load current. Vary the input voltage, increase or decrease, or the load current you vary, output voltage remains constant. Generally we call it as a stabilizer. You have seen the stabilizer in your house, almost the same thing this will do. It regulates the voltage. So from here onwards, if you listen to the word regulation, think that the output voltage remains constant irrespective of variations in the input voltage and the output current. Now coming to the circuit, here there is a current limit. Here we apply the unregulated input voltage. So this input is nothing but the output of the rectifier with filter. So it is unregulated. We connect here. We apply this voltage to a Zener diode. Zener diode symbol is this. Remember, always Zener diode should be in reverse bias to use it as a voltage regulator. Here there is one more current limiting resistance or series resistor. This series resistor is included in the circuit to limit the Zener current to a safe value when the load is disconnected. Suppose when there is no load, the high current should not flow through the Zener diode and spoil this Zener diode. So to limit the current flowing through the Zener diode, we use a series resistance or current limiting resistance. When a load is connected, the Zener current, the current which is flowing through the Zener diode, the Zener current will fall, because if you assume this is the current flowing at this junction, it splits into Iz plus I naught. So see, Is is equal to Iz plus I naught. If you remember the voltage divider rule, by applying the voltage divider rule, we can find the Zener voltage Vz is equal to the applied voltage, input voltage, multiplied by the resistance across which you are measuring the voltage, divided by the sum of the resistances in that loop. So Vz is equal to V into RL by RL plus RS. Vz is equal to, I need the voltage across the load resistance. So applied voltage multiplied by the resistance across which you are measuring, V into RL, divided by the sum of the resistances, RS plus RL. So you get this equation. To find the maximum value of RS, just rearrange the terms of this equation. You will get RS max is equal to RL into Vn by Vz minus 1. Simple mathematics. So you will get RS max. To find RS minimum value of the RS required in that circuit, let us consider the power dissipation by the Zener diode is equal to Pz. Pz, as you know, it is nothing but the product of voltage and current. So Pz is equal to Iz into Vz, where Iz is the current flowing through the Zener diode, Vz is the voltage across the Zener diode. So RS minimum can be found out when there is no load. Here in this circuit, assume that there is no load, that means there is an open circuit. There is open circuit. Now we would like to find out Rs minimum. Remember the Ohm's law, R is equal to V by I. What is V? Here the potential at this point is V in. Potential at this point is Vz. So potential difference is V in minus Vz divided by current flowing through that network Iz. So here Rs minimum is equal to V in minus Vz by Iz. Iz can be written as Pz by Vz. From this equation, Iz can be written as Pz by Vz. But here we have written Pz max. Why max? Here we are trying to find out the minimum value of the resistance. Resistance is minimum, current will be maximum. If the current is maximum, the power dissipation will also go to maximum value. So for that we have written Pz max. So rearrange the terms, you will arrive at this equation. So finally Rs minimum can be written as V into Vz minus Vz square by Pz max, where Pz max is the maximum rated power dissipation for the Zener diode. All diodes will have their maximum rating. The manufacturer provides the data sheet. In that data sheet, he will give the rated values. Then the output resistance, once again Ohm's law, output resistance can be defined as the ratio of change in the output voltage to the change in the output current. Delta V naught by delta I naught, or delta V out by delta I out. So where delta I out represents a small change in the output current, and delta V out represents the corresponding small change due to the change in the current. Then the regulation is given by the ratio of change in the output voltage by change in input voltage. Usually input voltage is also called as line voltage. Usually regulation is expressed in terms of percentage, so it is multiplied by 100. Regulation is nothing but the ratio of change in output voltage to the change in input voltage. Actually, if there is a change in the input voltage, the output should not change by any value. If it is an ideal voltage regulator, there should not be any change in the output voltage if there is any change in the input voltage. So 0 by something, definitely it should be a 0. Sometimes we need higher DC voltages. Whenever you are converting AC to DC, sometimes we need higher voltages, 2 Vm, 3 Vm, 4 Vm, 5 Vm, 6 Vm, etc. How we can get this? So here we will go for voltage doubler and voltage tripler. In the voltage doubler, the output voltage will be equal to 2 times Vm, 2 times the maximum value. Here the output voltage across the load will be 3 times Vm, 3 Vm. So that is the meaning of doubler and tripler. So output voltage doubles in the voltage doubler, output voltage triples in the voltage tripler. Now let us move to the doubler circuit. The circuit is as shown in the diagram. It is almost like a half-wave rectifier, but 2 extra things we have connected. One is the capacitor C2, the another one is the diode D2. C2 and D2 are the extra components that we have connected to get the voltage that is doubler than the half-wave rectifier output voltage. Let us see how this works. During the positive half cycle, this terminal is positive, this terminal is negative. Diode D1 is forward biased, so the current flows through D1 and C1. And C1 will be charged to the voltage Vm, because Vm is the maximum voltage across the secondary, so to the same voltage the capacitor gets charged. You may wonder why D2 is not conducting. If you observe, the cathode of D2 is connected to the positive potential, so D2 is off, D2 is reverse bias, D2 is not conducting, so C2 will not get charged. So during the negative half cycle, this terminal becomes negative, this terminal becomes positive. Now the current flows through C2, D2 back to the top of the secondary winding. I'll repeat, here it flows like this. Once again, this capacitor charges to Vm, upper plate positive, bottom plate negative. The current enters the upper plate in the beginning, so it becomes positive polarity, the other opposite plate becomes negative. If you measure the voltage across the load now these two capacitors are in series whose maximum voltage is Vm, so totally you will get 2 Vm. So we call it as a voltage doubler. Now coming to the voltage tripler circuit, the output voltage will be 3 times of the maximum voltage, that is 3 Vm. Now let us start analyzing this. During the negative half cycle, till now I started the analysis with the positive half cycle, but now I will start with the negative half cycle. Why negative half cycle? Initially I need to charge this capacitor. You should go for the half cycle where the capacitor gets charged. This capacitor gets charged during the negative half cycle, so start the analysis during negative half cycle. The current flows in this direction, so first it reaches this plate, so this becomes positive, another plate becomes negative. The maximum voltage is Vm, so this also gets charged to Vm. So this is during the first negative half cycle. During the positive half cycle, this becomes positive, this becomes negative. The current flow is through D2, C2, back to this. So the current reaches the upper plate of the capacitor C2 in the beginning, so this terminal becomes positive, this terminal will become a negative. To what voltage C2 will get charged? Here is Vm, here is Vm. Observe the blue marks, minus, plus. Here the capacitor C1 polarity is minus, plus. Minus, plus, minus, plus, they add. So here it is Vm, here it is Vm. So this capacitor gets charged to 2 Vm. C2 will get charged to 2 Vm. Now let us move on to one more negative half cycle, minus, plus. Now the current starts to flow through C2, D3, C3 back to the transformer. I repeat, through C2, D3, C3 back to the transformer. It reaches the upper plate of C3 first, so it becomes positive, this becomes negative. What is the maximum voltage to which this capacitor C3 will get charged? Now this is the half cycle, green, here minus, plus, here it is minus, plus, so 2 Vm plus Vm, 3 Vm, but go through along this C1. C1 polarity is plus, minus. Here it is initially transformer voltage polarity is minus, plus, C2 polarity is minus, plus, this is Vm, this is 2 Vm across C2, this is across the transformer secondary, this is through C2. Now next is Vm, plus, minus, Vm, this is the voltage across C1. So minus, plus, minus, plus, plus, minus. So 2 Vm plus Vm, 3 Vm, 3 Vm minus Vm, it is 2 Vm. So the capacitor C3 gets charged to 2 Vm. Capacitor C3 gets charged to 2 Vm. The polarities are like this. Output voltage is measured across the load resistance. That is nothing but across capacitor C3 and capacitor C1 connected in series. Voltage polarities are plus, minus, plus, minus. Here this one and this one. So plus, minus, it adds. This is 2 Vm, this is C1 is Vm. So totally it gets to 3 Vm. So this is the analysis of the voltage tripler. So if you know the analysis, you can remember the working of the circuit. The working is not given in your textbook. So go through this video, then you will understand the working of the voltage doubler and tripler. Remember, doubler gives you 2 times the maximum value, 2 Vm, here 3 Vm.